Hello, and welcome to Modeling Tribal Energy Sovereignty, Bankable Distributed Energy Pathways. This is our first presentation in this session. We really have two different portions or sections of the presentation. We will start with Guillermo Gomez, and like I said, Bankable Distributed Energy Pathways for Tribal Energy Sovereignty. So Guillermo Gomez is a senior technical project manager at Veregy, where he partners with tribal nations to advance their energy independence goals of efficiency and water stewardship. I'll let Guillermo share, more about his work, the work that they're doing at Veregy, and with the, tribal initiatives. So, Guillermo, the floor is now yours.
Perfect. Thank you, Trent. And yeah, thank you everybody for this opportunity. And as Trent said, I started my career as an applications engineer in the power generation industry. And around 2017, while working on some projects across Europe, I really became fascinated with microgrids and distributed energy systems. And that really led me back to California, where I wanted to focus on developing commercial microgrids. And really, that eventually shifted my focus towards tribal energy development. And what really made this possible is that I attended Zendi's course at UC San Diego. And ever since I did that, Zendi really became part of my toolkit, beginning in around 2017, 2018. And with Zendi, I've been able to really work on some interesting projects and really don't think I would have been able to develop any of those projects without such a powerful software tool. And so now, as we get into this presentation, which is really about modeling what's called tribal energy sovereignty, when it comes to tribal energy sovereignty, it really starts with one simple question, which we'll get to here in a couple slides. But the real is the this is a real tribal energy project that's been developed over multiple phases, and even though some of the details have been generalized, this is a real project with real lessons learned and real problems solved. And back to what that question is, it's the question really is, can energy sovereignty be engineered? Because something that we've discovered is that there is no optimization objective for sovereignty. There's things that we can optimize, such as cost, resilience, things like emissions, but we can't really directly optimize sovereignty. And I know there's people here from different verticals, and the specific vertical here is tribal governments. But I think that when you look at microgrids, this can ultimately be applied to other customers, and the way we're seeing the industry shifting to more resilient projects. And really, once I started working with tribal nations, I realized that there was a gap in the industry, and what that gap is that while many tribal nations are looking for energy independence from external utilities, they're looking for control, they're looking for ownership, they're looking for workforce development, and really long-term planning authority. But a lot of times, what the industry responds with is technology first solutions, such as whether solar or batteries or long duration storage or fuel cells or generators are the right technology. It really kind of starts more backwards than that. And although these are important objectives and inputs. They're not necessarily what it takes to focus on sovereignty. And so, really, I think we needed to start with what that definition of sovereignty is. And although every tribal customer and every tribal community that we work with has a different definition for sovereignty, we did our best to really define it with five dimensions, and those are governance, workforce, basically the ability that once the project is up and operating, you're going to have a workforce that can actually take care of this equipment and operate the microgrid. The other is planning authority, kind of a long-term roadmap for the community. What happens in the next generation, of of community of staff. What's going to happen to the project then, and then also just ownership and being able to own the assets, own the revenue, and having also dispatch control just in case the utilities are not able to provide power in the future. And so, once we really defined what sovereignty was to this specific community, we then needed a way to measure progress towards that. And so, what we ended up creating was a sovereignty ladder, and this really became our framework. So the goal wasn't just about installing equipment. The goal was how do we move through this sovereignty ladder and go from utility dependence and dependence on outside entities towards complete sovereignty. And and because and a lot of that has to do with sovereignty is not just about reducing costs. It's about having full control in the future and moving towards real capabilities of being completely sovereign. And what we see with a lot of projects, not just with tribes, but within the commercial and industrial government, universities, is that many projects kind of stop at this level too. How do we reduce costs? How do we control kind of one objective? And so we think that's where projects sometimes get stopped. And these projects that stop there, they reduce costs. They install assets, but sometimes what's not addressed is governance and workforce development. And so really, a lot of projects fail to optimize for sovereignty. So in the next part of this presentation, we'll really get into what this case study is. And to introduce that, I wanted to show some high level details. So this project involved a large casino resort on tribal lands, about 30 gigawatt hours of electrical load, 15 gigawatts of thermal load, 4 megawatt peak load, and about $5 million in annual energy costs. And something to keep in mind is that in California right now, we're seeing on average under the investor-owned utilities 10% annual increases. In 2022, we saw an increase of 22% in 1 year. And so, cost isn't the whole thing that drives this project, but it's a big thing because when you have an operation such as a casino resort, even if you throw in some assets and you're still utilizing most of your power from the utility, that power that you're getting from the utility is susceptible to large utility increases. And so but this kind of sets the stage of exactly what is the project that we're talking about. And there really was a timeline to this, right? This project didn't get developed overnight. There was a vision that came first, and that vision then led into uh, a development process, and the infrastructure eventually came. But for this tribe in particular, they were dealing with lots of issues with the utilities, beginning with the 1900s, really fighting for different resources. And in 2011, something that was really critical for this community was developing a strategic energy plan. And I tell a lot of tribes that I talk to and a lot of customers that I talk to that you got to start from a strategic energy plan. The strategic energy plan then led to a phase one project, which was a solar and storage microgrid project, and then a phase two, which is now under construction, which we're really focused a lot on what this phase two is on this presentation. And then the future development is we're working towards a tribal utility. And so I mentioned how, with the, cost, going through the roof in California, well, this phase one project was really awesome, and it brought kind of set the stage for energy independence, but you still had 80% of your power, being consumed from the utility. and really only 20% of local generation. And as these energy prices are continually going up, this makes it a challenge that for every time the tribe is thinking of maybe making an investment in new revenue generating opportunities such as EV, or maybe more slot machines or another event center, they're thinking about, well, the utility is going to take a bigger cut next year and a bigger cut then. So it really becomes an issue on, not just having resilience, but also just economic growth. If you've got 80% of your power being purchased from the utility, and so this became the baseline for phase two of the project. And in order to really start kind of looking at that um, phase two, it goes back to how do you engineer a process that takes sovereignty into consideration. And so the way we did that is first that community vision, that strategic outlook, and then really dissecting that into engineering requirements, technical specifications. What does the workforce need to look like? How many people do you envision to have on site as full-time employees taking care of equipment? So that was key. But the key part of this whole engineering pathway, and the kind of the glue that made all this happen was Zendi, because Zendi allowed us to then dissect these engineering requirements into specific pathways, right? And basically optimize and try each one of these pathways out until you ultimately get to a solution that can connect back to that community vision. But this took many iterations, and really without having Zendi to do that, and having, I mean, the team from Zendi available to answer questions when we got stuck in the model. I don't think we would have been able to do that. And the great thing about Zendi is that now that we've got all this modeled in Zendi, we can now take this into the implementation phase, into the control design, and we're also using Zendi for the controls of this project. So that really gave us, you know, really helped us make informed. Zendi really helped us make informed decisions, and it really helped us translate the project objectives into kind of real implementation steps. So on this next slide, we're going to talk a little bit more about how to go from objectives to requirements. So overall, we didn't start by asking what technology should we build. We started by asking what capabilities should we own, and technology became the outcome of those requirements. And then this led us to another separate question, and that question really was, what capabilities must we own? And so again, this goes back to the tribe was looking to operate locally, uh, train their workforce, provide an educational platform for their community, for their students that are graduating from college. And so all these things went into what is the right technology, right? If we go with maybe some newer technology, it's going to be a lot harder for the tribal members to be certified and to make their own changes. And so it wasn't just about cost, it wasn't just about reliability. There were just so many factors that went into the ultimate choice of the technology. And so, this presentation isn't so focused on the technology selections, but the technology for this project did end up being a cogeneration reciprocating engine that plugged in with the solar and battery. Because the other part of this was, for some projects, we are looking at doing some of the newer technologies that are available in the market. But one of the key things for this project was what happens in 10 or 20 years. Is the company that makes the equipment going to be around, and is the tribe going to be able to take on that work? And so that was a critical point, piece of this project. And then let's talk about I guess a little bit about modeling versus priority. So modeling is great for optimizing systems, but really the community has to define those priorities, and both are important. but they're not necessarily the same thing. And so we ultimately used Zendi to evaluate multiple pathways against these priorities here that are on the right side. So sovereignty, government, workforce development, and future utility authority. So we evaluated multiple pathways, not simply the technologies, and each pathway represented a different balance between economics, control, independence, and sovereignty. And really, the differences became obvious when you look at how they perform. And seeing how these perform, it was very critical to use the Zendi team for the modeling. So this was some of the modeling that took place for this project. As I mentioned, the new baseline became that 80% still purchased from the grid, with 20% generated on site. And so Zendi really helped us make this the new baseline to set the stage for the cogeneration part of the project. So this was the baseline from the solar storage, and then we get into phase two, which was modeling out how to, basically taking care of this baseline and creating on-site generation for this blue area, which is still the utility purchased amount. So we go into a phase two, and then we're using this cogeneration for uh, generating power on site, but also taking care of the thermal needs of the project. And these designs were done by the Zendi team, and we also needed a lot of help kind of figuring out and validating, how these assets are going to perform on different tariffs. So I'll pause here because I think there'll probably be some questions on this at the end. But this is ultimate the design results from this project. And as you see here, as with most kind of California microgrid optimizations right now, we try to utilize that battery storage during the peak time utility, but you've got the cogen running 24 hours. Perfect. Next slide. So we went from 80% of the power being purchased from utility sources to pretty much 100% energy independence, and really only 1% of the power purchased from the utility. And you still, with this project, we still plan on having that utility connection there, and probably into the near future. But there is a case for in the future, maybe 5-10 years, for the tribe to be, if they want to be fully sovereign, maybe they won't need the utility, or maybe they can just count on creating their own tribal utility. But ultimately, this was the end result. This is the end result of this project. That cogeneration system is in the construction phase, and so we're going to have a full microgrid with solar, battery storage, dispatchable cogen, and microgrid control. So this is really kind of a state-of-the-art microgrid solution to what's going on in California. And potentially this is a format that will lead to microgrid projects in other states, because the grid is continually getting more expensive. Power outages are no longer seasonable, and then you've got this huge influx of electricity usage from EV charging, the data centers. And so this is really kind of a state of the art approach to what's going on with the grid right now. So this is really kind of our roadmap. The phase one, that solar storage, kind of kicked things off. Phase two brings us to 100% independence. And then the phase three is that potential tribal utility authority and full governments. Commercial sector, you may not, need to get to absolute sovereignty, because again, tribes are looking at what happens, not just in the next 5 years, 10 years, but they're thinking what happens in 30 years, 40 years. And so they're all about, creating the capabilities in house to be fully sovereign. Perfect. That's to close my presentation, and now I think we're ready for some questions.
So we have a question from Bill Lemon. What is the required role of BIA in any tribal energy project? Does that role extend beyond the res for interconnection issues or other factors that reside in the larger geography?
Yeah, I think that I may not be able to answer that question. I can only answer really that question in terms of how it impacted this project, and there wasn't a role with the BIA in this project. And I think the reason for that is because we were dealing with a behind the meter microgrid, and we kept it all within reservation land, and so we weren't kind of expanding. We weren't creating new kind of changing land, for this project. It was all done within the existing casino resorts boundaries, and so BIA did not have a role in this. What was the other part of the question, Trent?
Does that role extend beyond the res for interconnection issues or other factors that reside in the larger geography?
Yeah, I can't, yeah, there wasn't, like, again, on this project specifically, we didn't have to deal with BIA at all. I will mention something about air permitting. That is a key thing. And even though this is on reservation land, this project, you still have to deal with EPA requirements for air permitting on this type of equipment.
Okay, great. Did you experience any supply chain issues? And how did you manage those to keep the project on schedule?
Absolutely. I mean, we're dealing with supply issues right now. Just having to get a cogeneration engine. We were able to get a 2 year, like almost a 2 year um, lead time on that. But what we're being told is, if you try to get one now, you're looking more at like 3 or 4 years. But with the switchgear and the engines, there's definitely supply constraints. There's the whole tariff thing, right? Having to figure out the tariffs with the changing landscape. And so the answer to that question is, yeah, I think and then we're also not, our company isn't necessarily, doing a ton of these projects. And so we're not buying a lot of this equipment in bulk. And so maybe due to that, we also get kind of longer lead times. But to answer your question is, yeah, definitely a critical piece. And we're looking at about 2 years for our longest lead time piece of
Mm,
equipment.
got it. To what degree was decarbonization a factor to the tribe in determining technology selection?
Yeah, it was it's definitely a factor, because especially you with the phase one, right? That was all solar and battery, but then with the phase two, the engines selected are engines that can actually be run on hydrogen, like they're ready for hydrogen. For power generation through hydrogen. And so there is that thought process of how do we reduce emissions overall. And this is going to sound kind of crazy, but overall, the times where the engines are running, which is overnight, is still producing less carbon emissions than the grid because we're running in cogeneration. We're running cogeneration, so we're using the exhaust from the engine to offset the natural gas that's used for the boilers for hot water. And so there is, even though we're using natural gas engines, there is a major carbon reduction compared to just grid emissions. But that is still a factor, although energy independence and kind of long-term sovereignty was the optimal method.
Okay. There are several other questions. We'll send those over to you so you can respond.
Perfect.
Since we are out of time now, we need to shift. But thank you, Guillermo. Great presentation. really good best practices, and good advice in there for moving projects forward with various stakeholders. So thank you for that.
Thank you.
All right, we will switch gears within this microgrid innovation use cases kind of double session that we're doing. I want to introduce you to our two speakers, two co-presenters. Um, they're going to be talking about scaling power for AI infrastructure and industrial electrification with lithium and sodium batteries. Tim Cali holds a Master of Renewable Energy and Sustainability degree from Penn State and has spent over 13 years advancing the renewable energy sector, and most recently is co-founder of Power Equity Group. And Dr. Wesley Zheng holds a PhD in battery chemistry, so definitely knows what he's talking about, from Stanford, and is the founder and CEO of POSH Energy, which is building a next generation power platform for AI and industrial infrastructure for battery storage to deliver clean, dispatchable on-site power. So, yeah, Tim and Wesley, the floor is yours. Take it away. Similar structure. I'll jump back in toward the end, and we can do some Q&A. Go ahead. The floor is yours.
Hi, everyone. I'm Wesley, and I'm the founder and CEO of POSH. So if you're in the energy space and you've tried to grow industrial load or building an AI data center these days, you probably have heard some crazy numbers about interconnections. It can take about 7 years to interconnect to the grid in part of the country, 7 years. And even in California, the energy cost has increased by between 50 to 100%, depends on where you are located. So it has been a very interesting time in the energy and power space, and we have seen an influx of project and inquiry. And in the next 25 minutes, I'm going to talk about how we are deploying some projects. Team from Power Equity Group will be talking about how we are using Zendy to model some of those projects and how we work together hand in hand to develop and deploy a project that I'm going to show you. So the talk will have two parts. The first half, I will talk about some of the project that we deploy and how we deploy it from the customers, from some of the architecture, chemistry selections, and the actual project that we have put on the ground. And Tim will take you inside the Zendy model on how we drive every decision before a dollar gets spent. There are usually two types of customers that we are dealing with. One is the traditional commercial and industrial customers. Think of manufacturers like cold storage, EV charger operators. For them, they have a problem with the electricity bill. The demand charge is going through the roof, almost by, again, 50 to 100% over the past 5 years in the PG&E territories. And the reliability of the grid is also been going down in certain part of the countries. A lot of them, they want to do peak shaving to reduce the energy cost. Some of them want to change their tariff. And that's where battery can play a very interesting role. Tim will talk about how some of our customers use battery energy storage to change to a more favorable rate tariff to help them reduce 20 or 30% of their total energy cost. On the right-hand side, it's about data center, and this is a more nascent but fast-growing segment where all of the data centers are looking at ways to not necessarily reduce the energy cost, but more about getting their project on the ground faster. Some of you probably have seen the recent news where Google just signed a 100 megawatt VPP program to help C&I customer deploy energy storage. And the goal is to make the grid more flexible and allow them to build data center in areas that are more congested. And that has been a trend that we are observing, where data center developers are paying other people to install batteries so that they can reduce either the cost of electricity for everybody and at the same time get a project permitted faster. This is a high-level overview of a typical system architecture for the project they were dealing with. On the left-hand side, you have the electrical grid, where you can have electron moving to and from the load. On the right-hand side, you have the facility loads, and then at the bottom, you have the flexible gens. In the middle is where POSH come into play, which is on the intelligent control layer. And we primarily do two things. One is provide the energy management system and the site controller to control the battery energy storage. And then we also provide the battery storage hardware that allow the load to be flexible and shift the load in a more favorable way for the end customer. I think the middle layer is where we believe is most critical in the modern electrical grid. And that's why we at POSH chose to play in this area. The intelligent orchestration layer is where we can decide how the customer's economics can actually show up and how we can make sure the load can stay where it is, but at the same time allow the grid and the load to be kind of talking to each other in a more intelligent manner. Why some of the customers are working with POSH? So we work really hard to make sure that we own the entire stack from load analysis, sizing, permitting, installation, demand management, and lifetime O&M. You're talking to one team. A lot of projects in this industry, they don't fail on equipment. They usually fail on like the handoff between three different vendors who sometimes don't talk to each other. So we kind of remove the hands off, and our project gets shipped within months, not years. And we are able to make sure that our customers are talking only to us and not like having to deal with multiple different vendors. And we provide a control layer in kind of two ways. One is a site controller hardware. The other one is the cloud management system. And we also provide work with third-party battery provider to build an integrated solution. We have our own SKU of the batteries, which is a 200 kilowatt-hour solution, 60 kilowatt. But we're also starting to work with third-party provider like Tesla Megapacks to help manage their load. And the goal is that we want to make sure we have full control of the entire stack and make sure the customers have project deploy that we can help manage as well, instead of having to deal with 3 to 4 different vendors. Here I'm going to talk a little bit about kind of the different battery chemistries on the market. I got a lot of questions from different customers, like what chemistry to use, what is a good type of battery chemistry for what kind of projects. I'd say broadly speaking, today on the market, 90% or even like 95% of project they look at is probably some flavor of lithium batteries, either LFP or traditional lithium-ion batteries. And these type of batteries are usually good because of high energy density, small footprint. At the same time, they are reasonably good with cycle life, and they've been proven because they've been around for about 20 to 30 years. The challenge is, of course, supply chain constraint, some geopolitical reason about constraint on the supply chain. At the same time, they also not great for extreme weather performance. Let's say you want to install a battery in an extremely cold, extremely hot environment. Lithium batteries are traditionally not great. The other chemistry that have been emerging and quickly catching a lot of attention recently is the sodium-ion battery chemistry. They are newer technology, but they are at a stage where it's already mass-produced. There are a couple of big vendors out there that are supplying sodium-ion batteries. In fact, we have a project in Singapore for a megawatt hour of sodium-ion batteries right now. Sodium-ion batteries has lower energy density, but it has much longer cycle life and much wider temperature window. And at the same time, the elements of materials used for sodium-ion batteries is less constrained by some of the geopolitics concern, and it's a chemistry that a lot of the big players are betting on as a way to supplement lithium-ion batteries for the next 5-10 years. I don't think lithium-ion battery is going to go away. I don't think sodium-ion battery is going to replace lithium, but I think it's going to become a significant it will probably carve out a significant market share for itself and play a supplement role in battery energy storage. And within POSH, we look at different chemistry. Our site controller and software can work with both sodium and lithium-ion batteries, and our control layer is agnostic to battery chemistry. And we work with both to hedge on the supply chain risk and at the same time to cater to the different customer requirement. Here are some of the projects we have done. Since the inception of the company, we have done over 100 projects, both on-grid and off-grid, big and small. We started with a lot of small projects, and now we are doing more industrial, bigger project in the range of 100 or a couple megawatt range. As I mentioned, we have a megawatt-hour sodium-ion battery project in Singapore, and we recently just did a 600 kilowatt-hour battery project for a big construction company in California. Here's a short video showing a recent project that we deployed. We did this project within about 6 months from signing contract to deployment. It was pretty quick, and we handled the project from end to end, from helping with the permit application to installation and commissioning. Next, I will have Tim talk about how we use Zheng to model the projects and how we able to size and get a lot of insight from using the Zheng tool. Just Tim.
Great. Thank you, Wesley. Yes, it's been a pleasure to work with POSH and learn from Wesley. So this was a neat opportunity here to look at a project that goes from a digital twin all the way to in the ground in well under a year. And what I'm going to do for you guys today, especially some of you new users who are going to be having your trial licenses, is try to help you identify some opportunities with Zheng and be able to look at loads. And I've done a lot to capture some of the screen shares from Zheng, so it looks familiar as you get into using the tool. I was once an academic user and worked my way into Zheng that way, so I know where you're at. So I'll try to make this simple and clear for you. So what we're looking at here, if you go back to that same slide, Wesley, back one. What we're going to observe here, identify loads that are good candidates for storage tariff. In this case, we'll be looking at a PG&E option S tariff. And because it's over a megawatt, we're going to be looking at a B20 option S tariff. And one thing to look at is your ratio of kW to usage in the load, right? We got about 1.758 megawatts of demand and 3.4 megawatts of load. If you look at a load and you see 4 times as much usage or more than demand, it may not be a good a candidate for a storage tariff unless you have additional renewables to offset the more expensive energy. Next slide, please. Okay, so what we can do is that we're diving deeper into this load and see if it is a tariff that if it's a load that has good potential for an storage tariff in a site that is not feasible for renewable energy. And what we can see, just kind of taking a look at a month here, is that the site looks like it works weekdays, and it looks like it's operating less hours. It's not operating 24 hours a day. It's not even operating 12 hours a day. So this could be a good opportunity depending on what time the facility is operating. One thing you do talk about with storage, for batteries is the load peaky? The load is actually not that peaky. It's only maybe got, 100 or 200 kW at the top here that it could be clipped, but is that really going to be, is that going to give you enough bang for the buck or not? We'll determine that as we go through here. So next slide, please. So in concept, in theory, right? What happens with these storage tariffs and different utilities around the country, but specifically in PG&E, Southern California, Edison has similar tariffs, is the utility will make a trade with you, and they will offer much higher energy rates in exchange for lower demand rates, with the battery being sort of the ticket to the fair, right? Ticket to the tariff. So in PG&E's case, you must have at least 10% of the capacity of the load covered by the capacity of the batteries. So since we had a 1.7 megawatt demand, we could get away with as little as 180 kW of battery to qualify for the tariff. Now, with only 10%, right, would that battery offset the higher energy rates? And that's really going to depend on when the energy is used. So if this concept makes sense, let's go ahead and move to the next slide. Okay, so understanding the load, let's first really digest the tariff, right? And as we look, we got to understand when is peak and when are the high energy rates going to take place in lieu of or trade for the lower demand rates across the whole tariff. So peak obviously is your standard 4 to 9. In the summer, we're looking at partial peak 2 to 4 and 9 p.m. to 11, and then off peak all other hours. In the winter, we're looking at peak at 4 to 9, same thing, and super off peak at 9 to 2 and off peak for all the hours. Next slide, please. So in understanding this, let's now start to digest the energy. And this is a snapshot right from Zendy. This is your tariff imported into Zendy and displayed in the different periods of time what the energy rates. So as we start to look at peak, off peak, or peak, partial peak, off peak, and super off peak, and then we look for the different seasons, right? Summer, winter, or they have a spring season. We can see that in peak, it looks like your energy is ranging from 13 cents to 11 cents, right? Partial peak, it's about 9 cents, and off peak, you're about 7 cents. So remember those numbers, kind of 13 to 7 cents. Okay, now we're going to take a look and go and look at the demand charges for the standard B20 tariff. In this case, it was B20P because it was interconnected at primary voltage, but those rates are very similar to B20, maybe a half a penny different or something like that. Oh, say next slide, please. So now let's take a look and try to understand the demand charge, right? First of all, big demand charge, $34, right? For non-coincidental demand. That's any time of the month. That's your highest interval. It doesn't matter what time, what period, whatever. $34. So we've got $34 times 1,700, right? That's a pretty big demand charge. And then we got additional demand charge for peak, right? Peak period, another $35 if you're in peak, and in the summer, peak in the winter, $2, and then your off peak, $8 and 0 in the winter. Okay, so now let's go and look at the rates within the P20 storage tariff, which is P20 option S. Next slide, please. Not to be confused with P20, B20S for secondary, but B20 primary interconnection option S for storage tariff. And your option R and option S has very similar, has almost identical. They are the identical energy rates. It's just, are you going to be having solar and battery, or just solar, or just battery, just storage? So what do we see here? What's happened? The energy rates have exploded, right? We've gone from 13 cents to 38 cents at peak. We've gone from 11 cents to 16 cents in the winter. Your partial peak is no longer 9 cents, it's 15 cents. And your off peak is no longer 7 cents, it's 21 cents. So big difference here. So obviously we've looked at that chart, right? Energy rates up, demand rates down. So now let's go take a look at what's the reward. What are the demand tariffs? Take a look. Next slide, please. Demand has crashed. $35 down to $11, right? On your non-coincidental, which is any time of the day, and then during your peak or off-peak periods, another $4, $5. So big difference, right? We dropped 3/4, 60% or so in demand charges. Next slide, please. Okay, so why could this work, right? Well, let's look at the behavior of the facility. Now we're just looking at a day, and we can see the facility shuts off about 3 p.m. and starts up about 6 in the morning, boosts up to their demand level, and then shuts off before 4 p.m. So this facility's already had modified their behavior for peak and off peak. It also happens to just work spectacularly with the option S tariff, because we are avoiding all those big charges, the 38-cent energy during peak, but we get to take advantage of the very, very low demand charges across all time periods. So how does this look when you actually start applying this to the load to the tariff? Next slide, please. Okay, great. So we're going to take a quick look at the B20 tariff versus the B20 option S tariff. No batteries or anything. Just what are we looking at? Well, B20 standard tariff, you're paying $380,000 for electricity or energy and almost $800,000 for demand, right? What happens if we just take the same load and swap the tariff? Let's do that test. Next page, next slide. Big difference, right? Energy's gone up a little bit. It's gone from $380,000 to almost $500,000, but demand's dropped almost $400,000. So we know this is great. Now we need a ticket to the tariff. How are we going to get that, right? We're going to use that qualifier of 180 kW of battery to qualify for this 1,758 kW peak demand load. Next tariff, next slide, please. Okay, so quickly, just to refresh a little bit here, right? Your total load, your total bill was $1.2 million, right? On your baseline. We already looked at those numbers. Next slide. Okay, so let's just look at batteries on the standard tariff, right? Great. We've got some savings here, and we're seeing the batteries are generating $71,000 with the standard B20 tariff. This is 3 POSH stations, 60 kW, 207 kilowatt hour batteries. Next slide. Oh, real quick. I want to go back real quickly, and you can see right there. We're breaking even at about 4 years, right? 5 years, we've got to break even. Not bad, right? That's good. That's good. That's good. That's a good project. Can it get better? Yep. Next slide. Okay, so now's that rate switch, right? Just rate switch, no batteries. It's not possible, but it's indicative of something to look for. And we can see, oh, wow, right? That we are saving $275,000 just from the weight switch, right? Energy up $118,000, demand down, it was $500,000. So we've got a net $275,000 swing. Obviously, works from day one, right? Didn't cost anything to switch rates, but we need a ticket. We need the batteries to qualify. Next slide. So minimum qualification of batteries, 3 batteries, option S. What do we see now? We see break even or payback in basically 2 years, right? Under 2 years. and we see a new total savings of $319,000. If you did the math, you'd notice that the batteries are contributing now not 71, but only $44,000. And the reason that it's dropped a little bit is demand is lower, right? So if we're doing demand charge management, but we're the tariff for the demand charges is lower, the battery is going to do a little less work, same amount of work, but a little less value. But it's so superseded by the value of the tariff that it's definitely worth it. Next slide. So why not more batteries, right? In this case, well, let's see what happens, right? So just as here's one test, right? 6 batteries. So we doubled the size of the system, right? This was really just getting batteries, is using them as a ticket to the tariff, right? We don't have solar energy to offset more energy charges. So adding 3 more batteries, doubling the size of the digital twin to 6 batteries, the resulted savings from battery dropped 43%. The tariff savings don't change, but the battery savings dropped. So it's only giving you $19,000 more savings for the capex of 3 more batteries. So in this case, and it's slowing down your return on investment, your break-even year. So 3 batteries was optimal. Next slide. And what was the outcome, right? We started at $1.2 million in total spend. We're down to $958 in total spend. We've got operational savings of 26% for very low capex, right? Three 200 kilowatt hour batteries, somewhere in the $600,000-$700,000 range, probably totally installed. And your IRR on this project, a whopping 66%. I don't think too many people are going to say no to an IRR of 66%. Last slide. Guess that's it. I think there was one more after. Is there one more slide? No, that's it. All right. Well, thank you. This has been a presentation by Power Equity Group in conjunction with POSH, showing you battery chemistry, specific projects, and detail on implementing a storage-only tariff at a specific load, what loads to look for, etc. So welcome. I encourage you all to take advantage of your free licenses. You can definitely find me on LinkedIn, and if you might even get a little bit of help out of me here and there if you got a quick question. So thank you very much, and it was a pleasure doing this presentation.
Thanks, Tim and Wesley. We have a really good technical question on the control side of things. So Giovanni Gallegos asked regarding the energy management cloud, predictive analytics, does the system combine your AI load prediction models with a dynamic model predictive control framework to optimize battery dispatch under real-time network constraints?
Yes. So the AI model is predicting the load profile in real time, and we adjust the charge and discharge and the timing of those events according to the load profile as well. And this is done. All our system ship these days with Starlink and is connected to our backend because we want to make sure we have the connectivity and get the data, and we have some GPU running in the backend, crunching those numbers all the time to make sure that the algorithm tailored to the specific site.
Makes sense.
I hope that answers your questions here.
There's some congratulating on the excellent IRR, so that's great. Also, as you're using Zendy for modeling, what was the rationale behind building your own EMS?
I think Zendy is a great tool for modeling. I think for the EMS is usually, as I mentioned, require high communication between the software and the hardware. And we have seen first, I'm not saying Zendy is not good, I'm just saying that we've seen previously other people trying to integrate different hardware with different EMS there's usually a lot of friction in the process. There are a couple of good examples out there of like standalone EMS software. It just we felt that from the customer experience point of view, it's easier if they are talking to one vendor who have full control over both the EMS and the software stack and maybe even the hardware. Tesla has done a pretty good job in this aspect. Like they have full control over like everything, and that's why a lot of people love the user experience because it's very smooth, and that's what we are trying to get to for CNI battery project is to make sure that the customer have a good experience in terms of um, getting the software and hardware to work seamlessly.
Yeah, and I think there's more that, our teams can talk about there too.
Yeah.
So that would be great. Um, are you are you mainly working with battery? Are you, doing projects with generators, other technologies as well?
We just started some power generation project. It's still in the early stage. Most of our project that deploys are pure batteries and solar. So it's either solar plus batteries or standalone battery project. We haven't done a lot of integration with other power generation like gas turbine and engines yet. We are just started because we have some data center customers that are looking for adding on-site power generation with flex fuel genset and batteries.
Okay, great. Well, I think there are a couple of other questions that, we can send along and you can respond to those. But we have reached a point where we'll go ahead and wrap this up. But thank you so much for the detail, for the walkthrough, and very insightful. And I think the participation in these sessions, toward the middle to depending on where you're at in the afternoon, have still been really strong. So we're excited to see that. Um, so with that, we will go ahead and adjourn for the day. Just from a housekeeping point of view, tomorrow, go ahead, everybody listening, go ahead and look at the schedule, make sure you're registered for the sessions you want to be. If you have any questions, let us know. But technically registration is closed, so hopefully you got into all the ones you wanted to. But again, if you have any questions on that or run into a problem, let us know, and we'll do our best to respond as we continue to run the event for the next 4 days. We have some amazing stuff ahead: Tuesday, Wednesday, Thursday, and Friday, so definitely chime in. Thanks again, Tim, Wesley, and
Yep. Thanks,
Guillermo.
Trent.
Great job.
Thanks, Andy.